So today I'm going to present two topics which are related to the wake effect characterization. So in the first part one, I'm going to present data-driven wake effect characterization for operational wind farms. And in part two, I'm going to present parameter calibration in physics-based wake effect model. So I guess all of you already know the wake effects. So for economic and other logistic reasons, a large number of wind turbines are placed in a small area called wind farms. So you can see a wind farm in one of the wind farms in Texas, and here this is the offshore wind farm in Europe. And interestingly, wind farm, there is a interesting phenomena called wake effects. Basically, performance of wind turbines is subject to physical interactions between turbines. And here, the wake effects in wind energy stands for recirculating wind flow behind wind turbines. So basically, when wind blows, say, south to north, the upstream turbines absorb the kinetic energy from the wind, and the downstream turbines do not have strong energy to convert. So the downstream turbines usually generate less power compared to the upstream turbines. And also the blade rotation of the upstream turbines generates additional turbulence, which kind of distracts the wind. So the downstream turbines face the increased turbulence. In this research, we use data from an operating wind farm offshore consisting of 30 plus turbines. And this is the layout. Due to the data confidentiality, I just modified the layout a little bit. And in this wind farm, there is one meteorology tower that collects weather conditions or environmental conditions, including wind speed, direction, turbulence intensity, air density, and humidity. And here, this wind farm is the layout is regular, and the distance between two neighboring turbines in the direction of the dominant wind flow is about 11 rotor diameter, and the distance in the direction orthogonal to the dominant wind flow is about 6 rotor diameters. So just to describe the wake effects, we compare the data from two turbines when wind blows from west to east. So the turbine A is the upstream turbine, turbine B becomes the downstream turbine. And here is the scatter plot from actual operating wind farm. In this wind farm, the x-axis is wind speed, y-axis is power generation. And black is the data, power data from turbine A, upstream turbine, and red is the power from turbine B, the downstream turbine. And clearly we can see that upstream turbines tend to generate, larger power compared to the downstream turbines. And although turbines exhibit similar power generation patterns in the power curve, overall it kind of shows a similar kind of S-shaped power curve. But there are turbine to turbine variations due to the wake effects. So to see the wake effects more clearly, let's look at the power variations when wind speed is around 12 meters per second. So here, this is each dot represents the power output from each turbine, and the darker, the higher level of power generated. And we can see that these upstream turbines generate larger power than the second row turbines and so on. But interestingly, we see this turbine-to-turbine variation when wind speed is around 12, which is the rated wind speed, a little bit slower than rated wind speed. However, power variation pattern is not clear when wind speed is low, let's say like 3 to 6 meters per second, or when wind speed is high, let's say around rated wind speed or above rated wind speed. So you can see that when wind speed is around 5 meters per second, most turbines generate very similar level of power. Similarly, when wind speed is 14 meters per second, then most wind speed generates the similar level of power, which is the rated power. So the reason is, when wind blows very slowly, then, wake effect is not really significant. So there is no strong power deficit in the downstream turbines. When wind blows strongly, so when wind speed is like, 14 meters per second or higher, then because of the pitch control, the upstream turbines do not extract the maximum level of energy that they can extract. So the downstream turbines have still have sufficient energy to convert to the rated power. So because of that, the turbine to turbine the turbine to turbine variation is not very clear. So in summary, wake effect or the power deficit is substantial in mid-speed range, but this wake effect is not significant at low and high wind speed. So there is some heterogeneity. And also there is the turbine to turbine variation differs or changes depending on wind direction. So here, let's say when wind blows from east to west, so 45 degrees, then these turbines become the upstream turbines. So here, if you look at this blue curve, we see the power generation in this row and this row, this row, this row, this row. And sorry, so if we look at the red curve, yeah, then the T1 to T9, this is the most downstream turbines, so it generates the smallest level of power. On the other hand, this becomes the upstream turbines, so they generate the most power. When wind blows in the opposite direction, let's say 225, then this T1 to T9 becomes upstream turbines, so they generate the most level of power, and then we have this decay. So overall, this power curve at each turbine depends on wind direction, and also we see different wake effect pattern across wind speed and also across wind direction. So to characterize this, we develop a data-driven wake model for operating wind farms and investigate how the power generation differs at individual turbines. So our goal is to quantify power curve and multiple turbines in a wind farm across wind speed and also the wind direction. So here, our goal is to construct the heterogeneous power curves, because each wind turbine has different power curve due to wake effects, and also the power curve changes depending on wind direction. And we decompose the power output into the global and spatial terms. So here, the global term, this is like a blue curve. This is the common power curve shared by all turbines, regardless of the turbine location. But depending on turbine location and also the wind direction, we have this turbine to turbine variation. So if the turbine I is the upstream turbine, then their power curve is above this common power curve. If this turbine is downstream turbine, then their power curve is lower than blue curve. So we decompose the power output into this common term and also the spatial term. So here, this G term, the first term captures the global pattern, and the second term captures the turbine to turbine variation or the heterogeneous wake effects. And each term has the parameters, and the first parameter in the global term is shared by all turbines. So this beta is the same for all turbines, but the gamma term in the spatial term is turbine specific. So for turbine I, we have unique parameter. And to characterize this global term, we can use polynomial function, but here, just to generalize, we use the spline function. And for the turbine to turbine variation term, or the spatial term, so here, this difference between upstream turbine and the common blue power curve, this is the S term, the spatial term. And we can see that this S should be large in the mid wind speed, but it should be small in the low, small, or high wind speed. So basically, this S shouldn't be constant. It should be a function of wind speed. So we capture this kind of heterogeneous power difference over wind speed by using this kind of functional form. This can be polynomial again, but we use the spline model. Here, the thing is this term, the coefficient of this function should be turbine specific. So for turbine I, we have gamma I. For turbine J, we should have gamma J. Okay, so each turbine has its own turbine specific spatial component. Then the question is how to get this gamma I. So let's look at this kind of layout. So turbine C, for example, here, it should have the spatial term. And this turbine C is affected by this upstream turbines, neighbor upstream turbines, and it also affects the downstream turbines. So to capture this kind of interactions, we use the Gaussian Markov random field. So basically, we formulate this coefficient as a function of the coefficient of neighbor turbines. Okay, so gamma I, we use the random effect. So this is we treat this gamma I, the coefficient, as random variables, and the mean of gamma I depends on the gamma values at the neighborhood turbines. And here the Cij, this captures the interaction in intensity between turbine I and J. So for example, with turbine C, this turbine, the Cij with this turbine should be larger than, let's say, the most like distanced other turbines. Okay, so to represent this kind of interaction intensity, we use this formulation. And we note that this interaction intensity not only depend on the distance between the turbines, but also it should depend on wind direction. So we have this kind of formulation to capture the dependency in the direction orthogonal to wind direction and dependency in the direction parallel to wind direction. I'm going to skip the detail, and I will present the results. So when wind blows from west to east, then we estimate the power curve at these 4 turbines, and here this shows the power curve. Obviously T8, the most upstream turbines, power curve is here, and followed by T16, which is blue, and then T25, and T32's power curve is in red. So this is quite intuitively match. This is quite intuitive, and also it matches with the data pretty well. On the other hand, when wind direction changes, so when wind blows from east to west, then T32 becomes upstream turbine and T8 becomes the downstream turbines. So T832, the power curve of T32 becomes this. So basically, the power curve of T32 changes depending on the wind direction. And this shows the estimated power output at one of the turbine T8 when wind speed is 12. Okay, so when wind speed is 12, depending on wind direction, its estimated power generation changes. So when the wind direction is 240, which is from west to east, then T8 is the upstream turbine, so it generates largest level of power. But when wind direction is, let's say, 330, then it means the wind blows from northeast to southwest. So T8 becomes the most downstream turbine. So it generates very small level of power. So you can see that there is large variation depending on wind direction at one turbine, at the same turbine, and when wind speed is the same. But in the case of this T21, for example, this is surrounded by turbines. So, in any wind direction, T21 is affected by wake effects. So it is a downstream turbine in any wind direction. So here, this is the power the estimated power output over all wind direction. And in all wind direction, it generates similar level of power. Of course, there is some slight difference depending on how many turbines, before me or after me. But compared to this power level for T8, you can see that there's no much big difference. And this figure shows the power deficit of all turbines in this wind farm. So, so we can see that this power deficit due to wake effects really varies across wind speed. So when wind speed is small or large, there is no big difference among turbines. But when wind speed is around 11 to 13, the power output difference among these 30 turbines are so different. And the power deficit ranges between 0 to 21%, which means when wind speed is, let's say, 12, then the most downstream turbines generates 20% less power compared to the most upstream turbine. So we can see that this wake effects can be quite substantial. And we compare the accuracy. So we compare the output, the estimated output with the global model, and which doesn't really which doesn't really consider this wake effects, but just estimate one single power curve for all turbines. And we can say that when we use global model, its RMSE or MAE and MAPE is much larger than the proposed approach. So by considering this kind of wake effects or turbine-to-turbine variations, we can reduce the estimation errors by 13 to 15%. So this is the end of the part 1, and now we move on to part 2. And part 2 discusses the parameter calibration in physics-based wake effects model. So the data-driven wake model, which I just discussed in part 1, is useful for operating wind farms. However, this kind of power deficit really depends on the layout of the wind farm and also the terrain characteristics of the wind farm. So the outputs from part 1 cannot be directly translated into other wind farms. Suppose when we want to design a new wind farm, we cannot really use the output from part 1. So, but however, on the engineering models, like the Jensen's wake model or other wake model, has been popularly used for estimating power generation levels in general wind farms, and they have been used for layout optimization or control optimization. So in part 2, I'm going to discuss how we can use the operating data to improve the accuracy of this kind of engineering wake model. So I use Jensen's model in this research, but the idea or the approach can be applied to any engineering wake models. Here in the Jensen's wake model, what it does is it estimates the wind speed at each downstream turbines. So just consider 2 turbines, but it can be generalized to multi-turbines. And we have this free flow wind, and depending on the distance, we can this Jensen's model estimates the wind speed. So this the wind speed at the downstream turbine when the distance is d can be expressed as this. And here there is this parameter k in Jensen's model, which is called wake decay coefficient. But and here the CT is the thrust coefficient, and manufacturer usually provide CT. But K is not observable, so there is no exact K value. In the literature or in the industry, there are some recommended value for K. Usually for the land-based wind farm, K equals 0.075 is recommended. For offshore wind farms, K equals 0.04 is recommended. But in our analysis, we tried those recommended K values, and the recommended K values do not give us quite good estimation. So in this research, we want to find good wake decay coefficients. And the reason we need to find good wake decay coefficient is because this wake decay parameter influence the wind speed deficit at downstream turbines a lot. So here, this shows the wind speed deficit along the downstream distance with different K values, with different wake decay parameters. And so suppose we use K equals 0.01, then this is the wind speed deficit. But when we use 0.1, then this is the wind speed deficit. So you can see a large variance. And which wake decay parameter is good? Depending on which one we use, the result is so different. So we want to find good wake decay parameters in Jensen's model. This is called parameter calibration. And parameter calibration aims to improve the accuracy of computer model, in this case, Jensen's model, by finding an appropriate parameter value employed in the computer model. So in the computer model, we have input X, like wind speed or wind direction, turbulence intensity, and we have parameter like the decay parameter, and output is the, let's say, wind speed or wind power at downstream turbines. And from operating wind farm, in the physical process, we also have data. So we want to find the wake decay coefficient such that the output from Jensen's model match the output from actual data. And to find this wake decay coefficient, what we do is we formulate the problem this way. So we look at the difference between actual data. So Yj is the output from actual wind turbine or wind farm, and Yc is the output from Jensen's model. And we want to find K that can minimize the difference between this computer model output and actual wind farm output. And here, because this YC, this is the output from Jensen's model, and which is like a black box. So this becomes really black box optimization problem. Furthermore, this YC is, this is not really linear. So this becomes nonlinear optimization. And in the nonlinear optimization, one of the most popularly used method is the gradient descent, which is, we can have initial guess of good K, and then based on data, we can update this K to minimize the difference between the Jensen's model output and actual power output. And there is some, iterative procedure to reduce the difference. And I'm going to skip the detail, but the problem is when we use the gradient descent, it has to run this Jensen's model with all the data points we can use. So if our operating wind farm has a large number of data, then let's say 10,000 data, then we have to run Jensen's model at least 10,000 times. But if this iteration takes 20 times, then it means we need to run Jensen's model at like 10,000 times 20 times, which is too much. So to reduce this computational burden, we can use the stochastic gradient descent, which means instead of running Jensen's model at every data points, we can randomly select a small set of data points, and then we update this wake decay coefficient. So we use this stochastic gradient descent, and here is the result from our approach. So we use the same wind farm. And in this case, we just use 1,000 data points, but it can be much larger than this. And we use 70% of data as training data, and we evaluate the performance using the additional 30% testing data. And here is the output. So for the offshore wind farm, the suggested K value is 0.04. And when we use 0.04, the normalized RMSE was over 100. However, from this calibration procedure, the optimal K turns out to be 0.1, which gives us 72 RMSE value. So by calibrating this wake decay coefficient, we can reduce the power generation estimation error by 35%, which is quite significant. Just so to summarize, in part one, I present a data-driven wake model where heterogeneous wake effects are quantified in a multi-turbine wind farm. And we discuss a new stochastic optimization method to calibrate wake parameter in the engineering model, like a Jensen's model, when the data size is large. And our case study demonstrates the superiority of the proposed method. We actually evaluate this method with additional wind farm, land-based wind farm, and we got similar results. And in the part two, we use Jensen's model, but this approach can be applied to any other engineering wake models. And we believe this approach can be useful for some decision making, such as wind farm layout design and control. So yeah, so these are some related publications, and thank you very much for your attention.
Thank you.